Okay, so we're getting ready for the third exam, and one of the topics on the third exam is sequences. So that's the kind of the theme here for number one. All right, so we have to say whether the sequence converges or diverges for these sequences here, A, B, C, D, E, F, G, and if it converges, give the limit. Alright, so first remember what converges means. So if you have a sequence that's described by, an represents the nth one here, then it converges if the limit of the an is a finite number. So what we're really checking for is we're going to look at the limit, and if this is equal to some finite limit L, then we're going to say that it converges. And if the limit doesn't exist, or if it's infinity, then we're going to say that the sequence diverges. So I guess I can finish writing this here. Okay, so even if you didn't understand this, I think you're going to understand it. We do 7 examples. So let's just start with A here. Let me copy the problem down here. So we want to tell whether or not this sequence an equals cosine squared n over 2 to the n converges or diverges. So all we need to check is the limit as n goes to infinity of, I could write an, but I might as well write the right hand side here, what it's equal to, right? So as n goes to infinity, and the sequence that we care about here is cosine squared n over 2 to the n. Okay. Alright, so let's think about this for a second. What's happening as n gets big in this fraction? You know that cosine just bounces between -1 and 1, right? That's what cosine does. So let me just show you the picture here to kind of recharge your memory. So it goes like this. Just bounces up and down between -1 and +1. Okay, but there's a square here. So that's going to make it just bounce up and down between 0 and 1. Right, so it's going to make it look kind of like this, right? This is kind of what cosine squared looks like. It's never allowed to be negative because a negative square is always a positive. So the numerator here is bouncing between 0 and +1. Okay, and what's happening to the denominator as n goes to infinity? It's growing really fast, right? 2 to the n grows really quickly. Oops. So, when n equals, let's just look and see what happens when n is equal to 10, let's say. So when n is equal to 10, then we're going to have something between 0 and 1 up here. So, I don't know. Let's just call it cosine squared of 10. It's not going to be anything nice. But just think of it as being a number between 0 and 1. And on the bottom, we've got 1024. Which is 2 to the 10th power. Okay, this is a really small number, right? What if we make it as big as possible, then we make the numerator 1, and then we've got 1 over 1024, and that is, it's approximately 1 over 1,000. So what's happening here as n goes to infinity is that this thing is going to 0. Thing goes to 0. If you want to prove it more exactly, I think it's obvious. But this is a nice chance for you to use the Squeeze Theorem, if you like the Squeeze Theorem. Because this sequence is trapped on top. It's trapped on top by the sequence 1 over. Oh, geez, it didn't help then, did it? Oh, that's nice. Okay, so it's always bounded above by 1 over 2 to the n, right? And it's always bounded below by what happens, the numerator can be 0. So if you think of this thing being on top, and then you have just this kind of this dumb sequence y equals 0 on the bottom. I know that's a silly sequence, but it's just the sequence 0, 0, 0, 0, 0. Bounding it below, and you've got 1 over 2 to the n bounding it on top, then there's a perfect chance to use the Squeeze Theorem, which says that in this situation, if a sequence is bounded between 2 sequences and the one on top converges and the one the bottom converges to the same thing, then the trapped one must get squeezed to the same limit, and so everything goes to 0. So long story short is that the answer to A is 0. Okay, all right. So if you got more confused as my explanation went on, just forget about everything that I said after you understood the answer. All right, so what does B have for us here? All right, so we have a little factorial notation and also a slightly different way of representing a sequence, right? So the brackets just kind of mean the same thing. So you've got these things, one for each n, and we're wondering what happens to this expression as n goes to infinity. So let's copy it over down here. You can write it in this notation if you like this notation better. So a sub n is equal to 2 to the minus 1 factorial over 2n plus 1 factorial. Okay. And so just like the last time, and just like every time, we're just going to take the limit here as n goes to infinity. It's going to be a lot easier if we do some simplification first. So you might be asking, how can we simplify this thing? So the factorial, it multiplies things, it just counts down, right? So let me give you an example just as a warm-up for factorial. So this is what it means. It means 7 times 6 times 5 times 4 times 3 times 2 times 1. So I'm just reminding you what the notation means. So even when the expression here is a little bit more abstract, it has an n in it, it's still just counting down. Notice that the one on the bottom starts at a higher place than the one on the top, right? So what I want to do is let the bottom one count down until it gets kind of to the same level as the top. So I'll show you what I mean. I'll just copy 2n minus 1 up here, factorial, and on the bottom I'm going to let it count down. So I get 2n plus 1 times, now I take 1 away, right, times 2n times 2n minus 1. And now I'm supposed to keep counting down, but as I do that, what's going to happen is I just have 2n minus 1 factorial left to go. All right. And now what's the advantage of that is I've got this nice cancellation here. So those two turn out to be exactly the same. So the whole expression is equal to 1 over 2n plus 1 times 2n. Okay. And now what happens here as n goes to infinity, we've got 1 on top, never changes. On the bottom we're going to get a bigger and bigger and bigger and bigger and bigger number. So the whole expression goes to 0. Okay, alright, so we've done the first two. So just to remind you, for A we got 0, and we just showed that the answer to B is 0 too. Alright, so push that stuff down. And let's look at C. Okay, so here is C. C is kind of interesting, so let's just set up the limit that we care about. We're going to be looking at the limit as n goes to infinity of natural log of n over natural log of 2n. Okay, alright, so there's no... Well, okay, so you have two choices here. One is you could use L'Hopital, and another way, let's do it this other way. This is the first way that occurred to me, is to use the laws of logs to rewrite the thing like this. You could do ln n on top, and on the bottom you've got, by the laws of logs, you can break this up into ln2 ln n, right? So times becomes plus with log. That's one of log's killer features. Okay, so what now? Now it's kind of obvious what's going on here, right? But if you want to really beat it into the ground, then divide top and bottom by 1 over natural log. Okay, so do 1 over ln n to top and bottom. And what's going to happen when you do that? So let me just do this multiplication. So when you bring it into this top place, you're going to get 1 in the numerator. It's going to distribute in here, and you're going to get 1 over... I'm sorry, it's not exactly 1, is it? It's this constant number, natural log of 2 over ln of n. And here it is going to give me 1. Okay, so what's happening here as n goes to infinity? You tell me. This 1 is just staying the same up here. This 1 is just staying the same. Here we've got a constant over something that's getting enormous. And so this little piece is going to go to 0. So the whole thing is 1 over 0 plus 1 is just 1. Okay, so this one is going to 1. Alright, so far nothing has diverged. All these sequences have been converging. Okay, so let's go on to D here. Alright, so oh my god, it's arctangent. So what is this one? I'm kind of freaking out. Well, if you just remember what the graph of arctangent looks like, it's really not so bad. So if you're one of these people, and I hope you are, who likes to memorize as little as possible, you could just remember the graph of tangent, and then remember that inverse tangent is going to be the same graph reflected across the diagonal. And when you do that, when you reflect tangent across the diagonal, it makes this shape, right? So just like at pi over 2, tangent asymptotically goes up to infinity, when you graph arctangent, as x goes to infinity, it asymptotically approaches pi over 2. Okay, and this is the graph y equals arctan x. Okay, and so let's look at the limit as n goes to infinity of arctan 2n. So basically what we're doing here is putting bigger and bigger values of n into arctangent. And so what's going to happen, it's totally obvious, right? That's what asymptotically means. It means it's getting closer and closer to this line. So the outputs are getting closer and closer to pi over 2. The answer is pi over 2. Okay. Alright, so that's D. So D is pi over 2. We're kind of smoking through these things. Alright, so what about E? Can almost see it up there at the top. So E is cosine n over 2. And I know that diverges. I'm trying to think of a good argument why. I mean, yeah. So I'm a mathematician, and so I'm groping here for like an ironclad, watertight explanation. But basically the reason is that you're going to be putting in integers and half integers into cosine, but those don't align anywhere nicely in cosine. What you're going to be getting is basically random numbers between positive 1 and minus 1, and they're not going to be settling down to anything. And so the answer to E is diverges. So finally we've got one that diverges. Okay. Alright, and what about F? Okay, so, right. So the F is a deceptively hard one, right? Because you really have to use the actual definition of the limit. Okay, so what are the limits of these numbers? So you don't have to reinvent all of mathematics, right? Thank God. But if you are going to, like most people decide, it's how they decide to take the test, is to reinvent all of mathematics rather than study. But okay, so if you're going to reinvent mathematics, then you might think, well, zeros are becoming more and more prevalent in this sequence, therefore the limit is 0. But that's not what the limit means. Remember, the limit means, so what does it mean for a sequence to converge to some limit L? It means that for any little force bubble that you put around L, okay, I can make this as small as I want, there's some cutoff point, like let's say right here, after which the sequence has to be totally inside the force bubble. Okay, so, and there's nothing special about that one. I can make those as close to L as I want. So the limit means that I could make a force bubble even this close to L, and there would still have to be some cutoff point after which all the things in the sequence were inside this little force bubble. Okay, so the problem with this here sequence is that it has ones in it no matter how far you go out, right? So you're never going to be able to trap it inside one of these little force bubbles that are smaller than 1, because it's always going to be popping out of the force bubble to go back to 1. And so f diverges as well. Okay. And g comes after f. And this one is really easy if you have absorbed this fact that the limit as n goes to infinity of some decimal number, by that I mean some number between 0 and 1, okay, like let's say, oh, I don't know, 0.2. So what happens to that thing as n goes to infinity? Just think of this as it's like taking 20% over and over and over again. What happens if you take 20% of 20% of 20% of 20% of 20% of your money? Then you're going to end up with nothing, right? This is 0. And so what happens to g as n goes to infinity is that this 1 gets left alone, and this part goes to 0, and so the answer is 1. Okay, so that's the whole deal. That's the end of number 1.